Today I want to implement hash maps in Plum, so I'll first explain how to do that conceptually. So I want to implement a hash map with closed addressing, which means that there's essentially just a big list of buckets. And these are just an array, basically, with a fixed size. And each of these buckets initially is empty. And when you put something into a hash map, for example, you store the entry, I don't know, 3, 5, meaning that 3 maps to 5 in the hash map. You take the key, the 3, you hash that into an integer. Maybe that's a 3, but maybe that's something completely random looking, like 142, I don't know. You take that modulo the array length, and that is the index in which you will store that. So let's say that is here. Then you store the map entry in here. And when you try to retrieve a map entry, for example, you want to know what is stored under the key 3, you can just do that same hashing. You hash the 3, that tells you the index in which you need to look at this list of buckets. And yeah. So you can efficiently retrieve the 5. Of course, there are a few practical considerations. The first is, what if that bucket is already filled? What you usually do is you just go to the next bucket. And if that is also filled, then you go to the next one, etc. The problem with that is that you get these kind of ranges in the hash map where a lot of buckets are filled. And because these are quite big, like anytime a new hash maps to somewhere within that range, that is also appended to the range. So with this is called linear probing. With that, you kind of tend towards these big blobs of buckets next to each other that are filled. So what I want to do is quadratic hashing, where you first look in the next bucket, then in the bucket 4 places ahead, and then 9 places ahead, 16 places ahead, basically the square numbers, because that spreads out the buckets a bit better in the case of collisions. The second practical consideration is that you need to at some point grow the array. Like this array of 6 buckets, 6 slots, it can't fit more than 6 items. And even with like 5 items, it is probably quite inefficient. Because if your array is filled to like, I don't know, 95%, then there will be a lot of collisions, and the benefits of a hash map, of efficient lookup and efficient storing of values, that kind of gets lost. Yeah. And yeah, the third one is like removing items, but we'll get to that when I implement that. All right. So in the standard library, let's just create a new file called map.plum. And then define the map data structure. And let's actually use the same imports as lists, because I think some of those will be quite useful. Not all of them probably, but yeah. Okay, we'll define a map type that consists of, that has 2 type parameters, a key and a value. The map will map keys to values, and then using 2 spaces. And this will store multiple things, so a struct. It will store the buckets, which will be an array of buckets, I guess. Buckets being specific to that key and value. It will also have a size, which is an int, that tells us how many of those buckets are in use. And that will kind of inform our decision of when to grow that bucket list. All right. Something else? Oh yeah, in Plum, types don't have associated functions. or methods or traits interfaces or something. Like, you just have first-class functions. So I think the map probably also keeps track of the function that is used for hashing the keys. So some sort of hash lambda that takes a key and produces a hash, an int. We'll figure that out later. And then also an equality checking function that takes two keys and produces a bool. All right, so hashing first. I think, yeah, I already have this hash file that I don't really use. And I'm not sure what was going on here. Let's just hash. Yeah, it uses like algorithms for kind of distributing hash values, aggregating these, kind of aggregating entropy into a hash. I'm not entirely sure about that. I mean, I could model something like that, you know, having some sort of hasher. Yeah, let's do that, I guess. Maybe. Nah, let's not do that. Let's just have I mean, the individual types will have hash functions. Let's define, first of all, a hash type, which will just be an int, actually. And maybe later on we'll have functions for doing something like this, kind of combining multiple hashes. Yeah. Yeah, okay. Yeah, and this is copied from Martinez, so the syntax and stuff doesn't really match Plum, but that's all right, I guess. Okay, so back to the map. This will return a hash. Hash being from the hash module, and that's just an int. But still, I think it's more descriptive, so that's cool. Then what we want is being able to create a map. I'm not sure about creating an empty map. That kind of requires first-class types, and there were some problems with that in the list module. So let's just for now say that you provide one initial entry, I think. Or we could try that. Well, let's say you have this map function that accepts key and a value type, and that returns a map. And what that does is, several things. We need buckets, first of all. And the individual buckets, they can be filled with an entry. And an entry is just something with a key and a value. So entry key value has a key k and a value v. Alright, and this is either filled or it is empty. Let's maybe switch those around. Or maybe not. I like this better. Alright. Yeah. Let's try to compile that first of all, and then we'll see where things go wrong. this compiles, that's nice. I wanted to look at creating empty arrays. Did I have a function for that? Not really. Basically an empty array of a first class type. Function parameters of the type, they have to be known at compile time, and they can be used both in value positions and in type positions. Yeah. And functions are basically like monomorphized over that, like specialized for this specific t that you pass in. So for arrays, I think we'll just want to do this built-in generate array function, call that generate array, with the length 0, and then a lambda that takes an int index and returns, well, crash. This is never called. But then we cast that to a t. Yeah. Yeah. Does that compile? That needs type, alright. And it needs crash. Fair enough. And it needs strings. Hang on, can we do this? I don't know. No. Interesting. I thought that would work. Arguments of the type have to be known at compile time. And t is a parameter. That should actually work. Let's see, arguments of the type have to be known at compile time. Yeah, resolve arguments of the type. And then if the type of that argument is type, then we do body.get p.type, alright. And when we compile a function, which is up here, then we actually push the type variables into the body. So for every variable in the function parameters. Oh, I see. Collect type variables. Not only of the types, but also if like this works in. What is that? Like in this kind of function. Within this function you can use t as a value. This kind of array of t here. However, in here, the types of these parameters, they don't even contain the t. yeah, we basically want to do the same for, you know, for every parameter that is of the type. The ID in here, is that used? Yeah, it is used, but only as that, I see. Yeah, let's just do that, I guess. So we compile the type, and then if the type is type, then we also define oh, I see. It has the type param and not the type. That's why things are not working out. So actually in the function body we will just define visible.define param.name.string. We will kind of redefine that using not, so this is not a param expression, but it's actually a type expression, similar to what we have over here. Yeah. All right. Let's hope that works. Okay, there is no functioning as in scope. That is correct. So let's fix that. I think there's like a cast module, and that has an as function that takes, hang on, some value of the type t, and then a t of the type. Apparently not cast, no. What is that called? Type, maybe? Yeah, here's the as function. Okay, that compiles. Pretty cool. And now does capturing these work? Let's see. In here, let's say that we put this in there, and this returns an array of t. That works. Nice. So then, in the map, we can kind of create a map using a key type and a value type. But then we'll also need a hash function and an equals function. The hash function will just be a k. No, that will be a lambda that takes k and produces a hash. And then equals will be a function that takes a k and produces a bool. Yeah. And then this is like an empty array of buckets of key and values. The size is 0, and then we have the hash function and the equals function. Alright. If one of these is missing, does that still type check? It does. Okay. Oh, I see, because the main the map is not included in the main file in here. Alright, yeah. That's more like what I expected. Some syntax errors here. Try to use workspace hash int, but that doesn't exist. Well, true. Do need to import int. Right. Empty array does not exist. True. Okay, yeah, this is exactly what I expected. Nice. So we also want the equals function available here. And let's grab this so we can put that on a single line. Very nice. So then actually putting something into the map. And that is the interesting part. So put takes a map of key and values. It takes a key. Hang on. Or does it take an entry? And we provide a really concise, cool way to produce an entry. Like what if we had this kind of function that takes any k, any v, and it produces a map, an entry of key and value by just putting these into a struct. And you could essentially, and I can even do that in the playground, you could do something like this. Boom. This is a map entry. Sure. Right, yeah. In here, in a map, we expect an entry, let's say. That is an entry, and then this produces a new map with that entry added. I know. It would be really cool to support ... as some sort of to-do thing that the compiler actually understands. Well, yeah, what we want to do here is we want to calculate the hash, first of all. And that would be map.hash, that hash function from the map, applied to the entry's key. Actually, let's first unwrap the key and value. So key and key value is the entry. We hash the key, and that is the hash. Yeah, let's return that. That's going to raise a type error, but still. Okay, so in the playground, we do need that arrow function, which will actually import from here, arrow on any key and value, something else. Map takes a key and a value type. Let's call this empty map. And let's just copy the signature, because I don't want to type that. Thing. Yeah. Return value, have that in here, not part of the signature. All right. Now we do need to import hash. All right, and then in here we can actually import the equals, the arrow function. Nice. Yeah, this results in a map entry that has a key and a value. Key being a string, value being an int. All right, that is pretty cool. Then, what else? Yeah, putting something into a map, how does that work? And what is that type check, first of all? It doesn't. It's just that this is an earlier error. I see. There is no function named hash in scope. That is true. But it's a field on there. Can we do that? Of course we can. Well, b is not a primitive. There's a weird error. This makes more sense. I'm not sure where that comes from actually. Okay, a function returns something different than its claimed return type. That is very true. It just returns an int now, aka the hash. Oh, I actually think that is like fine behavior. You know, I think it's fair that you just have to do that. Yeah, cool. Okay, so we hash the key. Then we let's try to reserve enough memory, similar to what we do for lists. Here we have this reserve function. Makes sure that the map can reach the target size without allocating. Yeah. Given a map of key and value with we have a target size. Yeah, this just returns a map. All right. So what we do is we have this let's see, so map.array.size. There's map.buckets size if that is less than target size. And here let's have some sort of max, fill percentage. And I think that's usually like 60 or 80% of the map. Let's go with something in between, I guess, 70. Yeah, in order for the map to still be efficient. Actually, let's go with 60, sure. Yeah. Then here we have required buckets given a size int. Yeah, let's say that just calculates size times 100 divided by max fill percentage. Yeah. That does mean that we need the, oh, we do have that. All right, but not the divide function. That's also important. Okay, so given the size, this gives us the number of required buckets. And also let's kind of, round that up to a power of 2. So if map.buckets.len, I think, is less than the target size, required buckets given the target size. Then we do generate array. Of the required buckets of that target size, round it up to power of 2. All right, and then each of these is an empty hash bucket. Actually, let's unwrap that here. Like so. All right. And we still need to copy the items over here. Actually, let's do this at the top level. If this is false, then we know that the map is totally fine. Otherwise, if this is true, then we do this. Could I have like an empty map with a capacity? And that just calls a generate array of the capacity with a function that just returns, and it takes an index and it returns empty as the bucket. Alright, yeah, and this empty map is just empty map with that key, that same value, capacity 0, hash, and equals. Alright. So then, these are the required buckets. Given a size, alright, and then reserving enough space for a target size, just checks if we have enough buckets. Yeah, if we do have enough, that's just the map. Otherwise, we need to create a new map. This will just be empty map. Using that key, that value, the capacity of that. All right. Yeah. And then in the put function, we can just unwrap the entry into a key and value. Fair enough. Also, maybe let's have a function for just putting a key and value directly in there. Maybe, oh, maybe not. We'll see. This is gonna hash the key first of all. Fair enough. Yeah, also it needs to call map equals map dot reserve enough for the target size, which is map dot size plus 1. Yeah, then we know that this map has enough capacity, so we hash the key, and then we just insert the key, just do that, you know, which means that we check the bucket at that index. Hash modulo no map buckets.len And if that is empty, then we can put our value in there. And actually let's kind of unwrap stuff here as well, like the buckets and the size and hash and equals, sure. Oh, then this is a bit more elegant. Alright, if that is empty, we're trying to compute the new buckets here. Then we just put the key in there. So that would be buckets dot set. Yeah. We set that to the entry, aka the key and the value. Alright. And if there is something in there that is filled, then we'll need to kind of retry. So I think we'll need some sort of put with quadratic probing with the buckets, and currently probe number 1 is the entry. And that is a function defined down here that takes buckets, which will be an array of buckets of key and values. It'll take the probe and it'll take also the base, probe index and the entry. And it will return a new array of buckets. It should support multi-line function signatures, I think. Would be helpful in this case. Alright, so put with quadratic probing. Yeah, that kind of is given the hash as the base. And what it does, it just calculates hash plus probe index times probe index. That's the quadratic part of quadratic probing. And then that returns as an index. Well, that modulo the buckets. Len. Yeah. And same thing as up here, basically. Wondering if I can kind of somehow kind of unify that. You know what? Let's go with linear probing first, because why not? Like, efficiency is not. This is something you can easily change later on. Yeah. So we've raw put something in some buckets. This is the index. We don't need this, and we have the entry that we want to put in there. Yeah. So this just tries to put that in the hash, at the hash position, like so. Yeah, and then here we just take, this is just index the hash, yeah. And then the index is the hash modulo the bucket's len. We get that whatever is at that index. If that is empty, then we set whatever is at that index to the entry. If that is already filled, then we call ourselves recursively with the same buckets, but then hash +1 and the entry that we want to put in there. Until at some point we find an empty bucket, which we then set so we can return the array of buckets. Alright, yeah. Then in here we want to return the new map, and that is that consists of the buckets being the new buckets, consists of the size being, well, the original size +1, and then hash and equals. Well, hash is actually like map.hash. And here's a big to do. Copy items to the map. Hash, and let's call hash maybe hash fun to make things a bit less confusing. All right. Cool. I like that. So we should be able to do something like this. And we want an empty map. I don't know, from string to int. Using a hashing function that takes a string and maybe it returns, I don't know, the length of the string. I should maybe add some string helper methods. Just, you know, just an idea. Yeah, then also a equality checking for strings, which we also don't yet have, I think. Okay, you know what, let's maybe create a map from int to string. And then the int will just map to itself as the hash. And comparing to ints works using the normal int comparison. That is our map. And then we can say map.put a map entry that maps 3 to hello. Expected. Oh, I see. Modulo is not %, but modulo is actually like a mod function. Yeah. Then set on an array. Alright, add an int. And then this one here, an entry. Oh, I see. we actually want to put there in there filled with the entry. Let's import empty map using key type and value type, and then a hashing function that maps a key to an int, let's say, and an equality function that maps two of these, true, true, which we'll also need to import. Alright, yeah, type, we also need that. Ooh, okay, yeah, put on a map of key value, putting an entry of key value, and of course that requires having an entry. Oh, and that's probably not exported, yeah, from the main function, from the main style library module. So in here, let's first of all export entry and export the put function, takes the map and an entry. Alright, try to use workspace test playground.map, but that type doesn't exist. Yeah, the map itself also needs to be here. Alright, we are getting there. Oh, here it's called hash fun, I see. Ah, yeah. That is stored as hash. Nice. Then as from the types, again taking some value of the type t, and then t, which is a type. Interesting. I mean, it compiles to something that then segfaults. Well. But that's at least something, I would say. Yeah, let's maybe continue implementing that. I don't know if that's the smartest move. So that's like iterating. There's another thing which I want to work. Yeah, let's also have a put function that takes just a key and value, and that should make some of the other stuff a bit. Basically, we do this. Yeah. Alright, yeah, iterating over a map, that's still an open question. And then down here, I kind of want to create specialized constructors for common map key types. In particular, I want to have something like empty map for ints. The int map only accepts a value type and returns a map from int to that value. And that just calls, well, empty map. Basically what the playground does. Yeah, kind of this. Empty map of int and that value. Then use the usual int comparison for those functions. Yeah. And you can imagine like having an empty string map also defined in the standard library. And even having specialized constructors for maybe creating a map from a list. There's something like a map that then accepts a list of like 3 to hello and 4 to hi. I don't know. That would be pretty dope. That would be really, really cool, actually. Yo. Something like a map that takes a list of entries from int to some value. And turn that into a map of int to that value by creating an empty int map and then adding the entries. Something like that. In general, like a put all would also be nice, I think. And then maybe something like that. Put all that takes an iterator. I don't know, just spitballing here. Yeah. I do like that. Yeah, but not today. And I do have this segmentation fault to deal with. Well, yeah, okay, no other errors are here, but they are not really the essential errors. Let's pass the key and value directly, I guess. Yeah. And at some point I could even offer something like this, perhaps. Map with 3 is hello, false, hi. That would actually be pretty concise. I like that. That is clean. That is so clean, actually. Wow. I really like that. Alright, but first. Well, are we like, let's maybe go through this and see what's happening here. So allocate something of size 8 that smells like a lambda closure that only contains a reference count. Oh, hang on, we can even like trim this down even further. We can say, oh yeah, this is probably this lambda here. And then there's another lambda right afterwards. Oh, look at that. 2 allocations of 8 bytes. Okay, sure. So 2 allocations of 8 bytes, then another allocation of 8 bytes because empty map calls generate array with another lambda. Alright, yeah, makes sense. Another lambda. That doesn't capture anything. True. And then we do this. Allocate 16. What's that for? Oh, I see. That generates an array of capacity 0. Default capacity. Yeah, true. Then, like that buckets buffer, that array, the underlying array's buffer contains a reference count and a length, so 16 bytes. That makes sense. And then we free all of that and allocate 18 for the output string. Alright, but what if we try to put something in there? Why does that not work? And let's even go with this one, maybe. Put 3 hello. Ah, true. So put that takes a map and then a key and a value separately. Oh, and we probably need to import that in here. Sure. Alright, that does not work. So we allocate something with size 16, that's the buckets array, and then we free the closure, the lambda's closure for like creating the buckets. All right, then size 21. That is a weird size. That is a really weird size. So what does put actually do? Okay, we reserve something of map.size, aka 0 plus 1. Okay, we do map.buckets.len, Okay, 0 is less than required bucket size of 1 would be 1 times 100 divided by 60. Okay, that is rounded to integers, that's just 1. Which is a bit low. That's actually anyways, okay, so this maybe returns 1. Fair enough. So then we do capacity is, we want to grow the map first of all. So we round that up to the power of 2 to get like a clean size. Alright. Rounding up to the power of 2. Round up is defined in here. And here the number is 1, the factor is 2. That's not really a factor, that's more like the base of the power. Yeah, and alright, so we call this function here recursively, where the current power is 1, the number is 1, and the base is 2. Is big enough? Well, we compare 1 and 1, they're equal, is big enough. So is big enough true, we return 1. Alright. So this just returns 1. The capacity is 1. Then we create an empty map using the k, the v, 1, hash and equal. Alright. So in here we do k, v, 1, hash and equal. Fair enough. Generate an array of capacity 1 using this. Okay, yeah. Does that work? Let's test generate array. I'm fairly certain I've tested that before, but not 100% certain. So let's say we do something simpler, like we generate an array of integers, of 1 integer, that is a 0. Well, okay, yeah, fair enough. We need to import and generate array. Okay, that works. That's good. Also, I feel like I tested that before, so. Alright, next step would be doing something that a little bit closer to this code right here. Generating an array of capacity 1, where this is a bucket. The bucket being defined as that. Oh, I see where the weird size is coming from. Because the bucket is an enum that has an entry with like key and value. That is all nice, but then this is, because this is an enum, this also stores a tag. Yeah. And we also have as that takes t and then type. Yeah, that is true, I guess. So this is a bucket between int and int. And actually between int and string, to keep that realistic. That works. Alright. So we're allocating 56 bytes. Let's see, 8 bytes. It's 8 times 7. So we have 8 bytes for the reference count, 8 bytes for the length of the array. And then there was one item inside. And that one has an int, first of all. Has a string, which is 24 bytes. And then it has, oh I see, a byte for the enum tag. That is rounded up to a multiple of the enum alignment when it's stored inside a buffer. So that's 7 words, aka 56 bytes. Alright, why doesn't that happen before though? Like in this case. Oh, hang on, there was actually going something on here. Whoa. Okay, let's see. We've allocated the array, fair enough. Then we've allocated 21 bytes, which is a weird size. Dot put. I don't see any allocations actually. That is weird. Okay, so we're allocating something. And then we are freeing probably the original buckets, which is expected as we are not copying over any data right now. Then we allocate 8 bytes, we allocate the 56 bytes, we free the 8 bytes for the lambda used to generate the items of this lambda, of this array. But where are those 21 bytes coming from? That is weird. Nope, I don't get it. I don't get that. And it's a weird position actually, like push int. Oh, of pointer dot star, I see. doing something. I'm going to stop that for today and debug that some other time. Alright, I think the best way forward is to just go into and like fix simpler stuff and get a more minimal example than a map. And one option would be to just look at lists, create empty lists and see if that works. Because maybe something is wrong with this kind of type, first class type stuff after all. I'm not entirely confident in that. So let's do that first. In the playground, let's just create a list instead of a map. I don't know, using 1 and 2 and push a 3. Oh, I forgot to do that empty list of it. Yeah. Alright, that does not work because there is this, the as function is not in scope. Fair enough. As accepts a t and then a parameter named t of that of a type. Yeah, empty list needs to be imported, that's totally fair. And that's in here, we need to export that. Alright, yeah, and then import that in here. Alright, that worked. That's pretty cool. Yeah, can we maybe also work with strings? Kind of make sure that there's the list. You know what, that's maybe let's join the items. Okay, these are integers. Let's map the integers. By formatting them and then join them using commas. Okay, yeah, so format that takes an int. We want that. We also want map. That takes an iterator of t and a function that maps an iterator of a, I think, and a function that maps a to b. Yeah, and that means we also need iterator. All right. No. Bunch of function named map for the argument. Oh yeah, this is an array. We need to iterate on that. Yeah, let's maybe push that on multiple lines. Like so. Yeah, iterating on a list. I think I've done that. I need to import that. And then join iterator of string. And a string. All right. Phew. Okay, so apparently that join function doesn't really exist. Let's create that. Yeah, that will be, well, it depends on the iterator. Oh, no, hang on, we do iterator.intersperse, something like that, yeah, intersperse. Yeah, joining without a separator. And that just does iterator.fold. Yeah. Starting with an empty string, and then we have a string and another string, and we map that to a plus b, and that does mean that we need to import plus for strings. I would probably need to export that from the standard library. Intersperse with the separator. All right. Well, that is something. All right, we are compiling some function. And then some other function, and then some other function. First of all, we print compiling stuff somewhere. Oh, here. In toast to egg, I see. Let's maybe print the egg. Well, yeah, that is a lot of stuff. let's maybe print which functions are being compiled. And when converting that to the yogurt. Alright, in filter map. We are compiling map because we want to map this iterator of items of A using this closure, and we want to map from ints to strings. And to do that, we compile filter map. Alright. Very strange. Filter map. Let's look at filter map. I'm pretty certain that worked at some point, so that can't really be it, I think. Can't seem to find that. Oh, iterative filter. Let's pipe that to a file. Alright, here we go. So now what is expression 8? This takes two arguments, 0 and 1, fair enough. Then here we have a 2, we have a 3. Then we have a lambda. We call iterator next. That gives us expression number 4. And then here we reference expression number 8. That doesn't make any sense. Let's look at the code of that. See, this is some sort of And using the pattern broke things. Well. I see. I think in here we also have compile pattern. Yeah. How does that work exactly? I think we compile these field values. And here we do body.push. Which is an egg body builder. And push creates a new expression and pushes that to its children. Oh, hang on, is the bodybuilder not mutable at some point, maybe? Now this is a reference to a bodybuilder. That does look correct. Alright. We get the struct fields. Now let's look at this one more time. This is the we are calling some lambda, first of all. Oh, that's just in the wrong place. There should be in here. Like when that lambda returns more, then we want to extract the item and the rest. I see. So this is just returning the wrong, using the wrong body basically, the wrong body builder thingy. I see. So in the switch in here, we have a case body. And this should compile the pattern into the case body. That does make sense. Okay, invalid free. What is that? Is something with A0. That was allocated here, maybe? Is that the same? Yeah. Yeah. But here the size is 16 suddenly, and not 32 anymore. Yeah, that's bad. Oh, and this is just happening with lists now. Not even, we don't even have maps. Let's see. In the main function, we iterate over a list. Let's simplify the code a little bit at least. Does that still fail? Yes, it does. How about I'm wondering if this has anything to do at all with the actual list, or if that's also true for, you know, ranges, you know, like 1 to 10, some range. Yep. Yep. Right. What if we don't join this? Then it compiles. All right. I mean, join is internally implemented as intersperse and then join. Same thing. Ah, right. That doesn't exist. I see, because that's probably not exported from here. Oh, it does have interspersed with an iterator of A. I should really look at imports and exports. There's a kind of cursed right now. Okay, so there is no matching function named join. This function doesn't match the types. So this is a lambda that is empty or more with a rest that is recursive, and item being this one. No, hang on. Ah, right. We do need join iterator of string. All right. What if we comment that out? That works. Okay. What does join actually do? It just concatenates strings, right? Does that even work? Hi, you. Always, like, I'm almost hoping it doesn't. That would kind of simplify a lot of stuff. That does work. Okay. I just don't get it. What if I just had a list containing 1 and 2? Then I would need to format these. Alright, I can work with that. How about I don't intersperse these? Alright. I'm getting somewhere. Alright, so let's inline some stuff maybe. Invalid free. Yeah, that join is quite complicated, I think. Let's instead just do this directly. Yeah, true. That does require that I have the fold function in scope. It takes a t and then, well, first of all, an iterator of t, then a t, then a function that reduces that. Probably takes an a, maybe? Yeah, a. Oh, and a state, I see. Because these can be different, yeah. That makes sense. Okay, still fails. Now let's let it fold and try to simplify that. By just copy pasting that in here. Instead of importing that. I'm just trying to get a minimal reproducible example that crashes. Yeah, let's see if this works. Oh yeah, then we need next on iterators. Okay, but apart from that, that still fails. For the folder, rather than passing that around, we can just not do that, and instead kind of specialize this to an iterator of string and kind of get the initial state and add them directly in here. Then I could even call this join, maybe. Well, I don't know. Still failing. That's cool. All right. Now to creating a list and iterating on that. And that's basically this part. Oh, no. That's this part. A list with 2 items does this. That creates an empty list, and that reserves something on the list. Yeah, and that means we need a lot of functions now. We need crash using a string. We need to generate array. Oh, we already import that. Yeah, let's just see what it complains about. Array.len. Yeah, so len of an array of t. And that also means we need arrays now. Alright. Less than power off. Alright. Round up to power off does not exist. I think it should. Probably don't import that. Round up to power off. No, that accepts 2 integers. As does this one. Alright, we have get maybe. Let's actually just copy that maybe. I don't know. Now let's import that. Copy that in here. Okay, maybe on an array and an int. Function probably needs to import that from array. Oh yeah, dot else. That's pretty cool. That's the thing on maybe. And we want to import that here. That requires a maybe. Alright, that is still failing. Now let's specialize that. Let's say we are just inlining this in here using 1 and 2. Yeah, that is supposed to be a list of strings. Yeah, okay, envelope free. Fair enough. No, we don't need that anymore. We don't need to return that, maybe. Let's inline that. Actually, can we maybe simplify that? Can we just say, you know, list, and we immediately generate an array of size 2 by formatting the index. And just don't push stuff in the list. Okay, still same thing. Because then we don't need this anymore, we don't need this. Okay, now we're really getting to the bottom of this. Yeah, iterate is still a big one. Iterating on lists. that just returns a lambda. Let's maybe print that some other way. Let's say we join list.iterate, that one, same thing. And then that is the same as this. And that is the same as, oh, this is recursive. Well, there is no matching function named get maybe. Why is that a yes, is a list get maybe. A list get maybe is defined in here, but we can just import that. That does mean that we need contains now. Yeah. Reducing an example is a lot of work, but it is a way to like generate something that to kind of figure out where the error is. Let's list slice. I see. And then the length of a range. Then we need minus. Okay. Okay. That's good. Now we can probably inline a bit more. For example, this contains in here. That really just calls this, which then does this. So we could just, replace range start with 0 and range end with list.len, and the index is the number. And this makes sense. We check that the index is larger than 0 and that it's less than the list length. Oh man. Still fails with even less code. Where do we use that range.len in here? Yeah, let's use that directly instead. Okay, then let's hard code join for the iterate function on lists by basically inlining this. Yeah, so join doesn't no longer expects an iterator of strings, just a list of strings. And then it does that. You know, it has this lambda that it calls .next on. It switches on that. Yeah, and then here it calls on the rest. Yeah, let's not iterate on that either here. I'll just directly return that. Kind of like that. Okay, this is a lambda that returns empty or more of that. Oh, I see, it complains at the next function here. Yeah, I guess let's just call that. And yeah, that requires the call function. All right. Still same error. But now we don't need iterate anymore, so that has been inlined below. Very nice. All right. Can we maybe simplify this even further? We have a lambda, and then we immediately call that. Let's remove that indirection. All right. And then in here we map none to empty and some to this more thingy, and then here we switch on empty and more again. So we can just merge these two switches and just immediately, if this is none, rather than returning empty, we just copy this in there. And in here we just do that basically and return that, with more being, well, with item being first and the rest being that. All right, yeah. Then get maybe, I think that's only called down there. Yeah, so that's inline that. Get maybe on a list. Yeah, and the index is 0. All right. pretty cool. Now, 0 larger or equal to 0, that's always true. So let's just remove that. 0 is less than the list length. Indeed, that is a nice check. Cool. All right. Here we have slice on an array. Let's inline that. List and a range with list being in scope, and this is the range. Very nice. We don't need this one anymore. All right. Yeah, here we map on true and false, and map that to some or none. And then here we take that and do something with that. So that's just immediately false maps to none. So let's remove that level of indirection and map true and false directly. All right. Oh, now it's different. Now it says crash. Hang on. Yeah, here is a segmentation fault. No address available. I mean, in the false case, we return none. And then when that's none, we return initial state. They're even more fine-grained. And in this case, we basically create the value, that is that sum thing, and then we switch on that. And if that is sum first, then we do something. So what if we just do that directly in there? That works, okay, crazy. So that results in a crash now, but in kind of a, the crash instruction was called. But that is potentially a valid program now. It doesn't have the bug anymore. That is weird. So let's not do that. Let's keep that. Sure. We can still simplify stuff here. So let's inline that. All right. Still seg false. Here we do array.slice with that range. Let's inline that here. And the range end. Well, that's actually get like start one, and this is then, and then this is just start to end. But in here we can immediately use these, like so. All right. Pretty cool. Then this is that. we're getting pretty minimal here. Okay, now, maybe one more thing. This is basically a list with an array with a certain size, and then it has a length. That is the same size. What if this was just an array directly? Yeah, and the rest is just that sliced array. Please, yeah. Okay. No lists anymore. That is nice. Cool. Can we simplify this? Just say hi. Okay. No informatting required anymore. Then getting something from an array, that is actually a built-in, I think. And here, and is only used in here. So let's put that in there. And start is only used in there as well. So let's do that. Then I take that and I join that. This really doesn't do a lot of stuff, you know? Now let's import some built-ins directly. So rather than doing len here, let's import array len. The built-in for getting the length of an array. And just use that in here. Maybe even store the length. Array len of array. Alright. Yeah, let's also use int and string from there. Yeah, we no longer use lists. Or plus, for that matter. Or some sort of map stuff. Or even bool. Yeah. Now do we use type or entry or map or put? Generate array, we can use that from the built-ins. Oh yeah, built-in string doesn't exist as string, because a string is defined in here. iterating on a list, nope, on this, nope, join to range, nope, not needed, interspersed join, no thank you. Okay, fair enough. Okay. I'm trying to not depend on the standard library anymore. This is not used, this is not used. This, we don't use iterators. Yeah, array of t, that is also defined in the built-ins package. Maybe, I think we don't use that anymore. All right. Let's use array get instead of the get from the standard library. All right. Yeah. Slowly we're getting there. Here we still have ranges. Let's instead just do start as 1 and is len, and then use a slice that takes some start int and an end int, like so. Right. And that slice really just calls array slice. So right. Now the only thing remaining is plus for strings. Which uses concat from arrays. Oh. And that again uses copy. Okay, let's define range maybe. Range. Let's hardcode that for ints. That's just gonna start, fair enough. Yeah. Mm-hmm. Sure. There is complexity lurking in so many places here. Okay, we have get. Get is this one right here. It's actually array get. Sure. And this is array slice, where the start is 1 and the end is source.array len. Yeah, we do need array set. And there is no matching function named plus for ints. Well, ooh, why is this so much work? Add ints from the built-ins. That is what we want. Now we need ordering. Alright, that compiles. Pretty cool. And we now have a plus of strings in here. How does that work? Okay, we only use the standard library for the less than function. Let's get rid of that as well. Ooh, an example that doesn't depend on the standard library. Very nice. Pretty cool, actually. So here we have is empty, and that's only used in there. Let's inline that maybe. Is equals equals means just switching on that. All right. This just calls compare ints. Oh, hang on, concat doesn't even depend on copy. Just realizing that. I think. Yeah. Have like 60 lines of something that doesn't depend on the standard library. Nice. Let's call add ins here. And here let's call sub ins. Then we don't, okay, here add-ins as well. Then we don't need this plus function. And this minus function. Oh. I see, that was this plus function. Yeah, right. Prefix and first. All right. So where's the equals function used? Nowhere, I think. Let's remove that. Very nice. 50 lines. Phew. Use the last function. Let's inline that as well. 0 and len. All right. Can we maybe merge these two? So if this is true, then we'll just result in that. Otherwise in none, and then we don't need this mapping anymore. Okay. Yeah, same here. Okay, so in the end we call, let's kind of transform that. In the end we call join on that. Yeah, and on that. Pretty cool. Mm-hmm. Let's try to do that, to inline even more. So this join here, let's specialize that for the concrete value, and constant fold that. So here we have join 0, let's say, that we call with an array of length 2. That contains 2 times height, and that's kind of omit the array here. Yeah. Oh, let's keep the array, sure. But we know that this array only contains height 2 times. And that's why we know that the length is actually 2. And that the prefix is empty. All right. And then here we call join again with the array slice from 1 to end. So there's only 1 high in there now. So let's do that. Join 1. Actually, let's call this join 2 because the array has a length of 2. Here it has a length of 1, which is this. And then we can specialize parts of that again. And then here we know that the array is empty afterwards. So let's create another version of this function that works on an empty array. Yeah, we know that the prefix at this point is empty, at this point is high, and at this point is high. Should be able to just do that. Yeah, let's make these still accept a prefix, I guess. even though we don't use that. Like, constructing the prefix may be what causes the error. So. Yeah, here the prefix is empty. Okay, that's cool. And now we can kind of simplify these, because we know that compare ints of 2 and 0, that is actually less. So I think we can just do that. Switch on that, we know that this is sum first, but let's not do that for now. I know, but none can't exist, so let's only have the sum case here. Okay, still the same error. And this then calls join 1, where the length is 1. That is less, so this is just that. Alright, and that calls join 0. We know the length is 0. Which we know this is equal, aka none. We can just remove that. Okay, yeah. So rather than this one kind of generic function, we now have 3 specialized functions. Making this a little bit longer again, but also opening up the potential for, you know, better, more optimizations. Like in this case, we could just say this is an empty string. Nice. So we know that this right here is just an empty string. Can we just do that? Oh, hang on. That's not quite correct, actually. Oh, I see. Here we are joining that. Already. I see, with the prefix high and first. So this is actually the prefix, which in our case would be that. Yeah, I see. But I mean, if this also causes an error, we can just use that. Just changes the semantics of the program. Okay. How about we don't get anything from the array, and we just return an empty string directly? Beautiful. So first is something. How about we do that? Okay, that is different. Now there was a crash. So for some reason this some construction and then switching on that is relevant, which is weird. What if we do that? No concat anymore. Nice. mean, this just returns an empty string. Now that's kind of getting ridiculous. We don't need that binding, do we? No. So this doesn't really do anything useful now. Let's also remove the prefix here because that's not even used. Alright. Yeah, we don't use any sort of ordering or bool or range. Oh, yeah. Or slice. Okay, if it's on a single page. Now that's pretty cool. Array get, we don't need that. The length, we don't need that. Byte, not needed. Comparing ints, what for? Oh, because of that. Yeah, okay. We may need bytes. Is the same true for an array of ints? That works. Interesting. Very interesting. Huh. So a string is an array. See, so it's an array of arrays, basically. What if the array has a length of 1? Alright. What if we inline that? What if, rather than having a separate function, we just create the array? And we create sum and we switch on that. Okay. What? I mean, this is pretty minimal. Could even inline that because it's only used a single time. Sure. Yeah, but apart from that, I think this is as minimal as it gets. Mm-hmm. 9 lines of code that cause a stack fault. Okay, I guess let's debug that. Like, let's see whether these functions seem reasonable. That is a lot of code for so little stuff inside. Okay, so the egg is pretty minimal. We create a lambda that always returns high, and then we call generate array with a 1 and that lambda. We create an int, we call array get. With that array, alright. Yeah, adding dupe and drops I drop the argument to the main function. This is the waffle. You're dropping a buffer of bytes. Let's see, we allocate 8 bytes, that's a closure without any content. Then here we kind of allocate the buffer, I guess. Maybe. Yeah. That's a reference count, the length of the buffer, and then enough space for a string, which is 24 bytes. Alright. Then we allocate 18 bytes. That's the string high. Then we free the original closure. See, here we are freeing the outer array. But hang on, before doing that, we should have freed the string itself, shouldn't we? Like, I think stuff goes wrong in here. You dropping a buffer of bytes. Maybe. Like generating an array. Let's maybe print the instructions. I don't know. We already do have some code for that, I believe. Yeah. Or at least the code. Dang, that is a lot of stuff. I'll ignore all the C, the control instructions. This allocates memory. The D ones are the interesting ones. D3 was like storing something from into memory. Probably the length. The reference count of the closure. Yeah. Then here we allocate more memory for the actual array buffer that backs, for the buffer that backs the array. We store a reference count in there. What was F2 was call, I see. We store a reference call in there, we store a length in there. One item, yeah, then we call the initializer. And that then was D5. Loads something. Sure. Loads some more stuff. Then it allocates enough space for the items, yeah. It stores a reference count and a length in there. And then it stores bytes. I mean, here we are freeing the closure. And then the next step, what we do is we've kind of successfully done this part. Then we array.get. And that loads something, and then a bit more, and a bit more. It's probably the 3 bytes representing the string. But then it loads a bit more, stores something. Where do we free the original array? Because that's definitely happening. So we get to this point. We dupe some string. Alright. We drop the surrounding maybe. Sure. We drop the contained string afterwards. All right. And then we allocate some more for some reason. That's weird. For an empty string, something like that. Huh. Yeah, for an empty string. That's weird. That is weird. Hang on, where do we free this one? Here we dupe the string inside that. We create an aggregate, generate array. Yeah. Right. Oh, I see. Then we call it array get. I see. And that consumes the array. Okay, so that original array is freed, and here we return an array that was stored in there. Array get. Let's look at that. Array get. Oh, I do have a suspicion. Maybe array get doesn't dupe whatever it returns. So when the original array gets dropped, we also drop this contain string. Oh, let's see. So we have main, and we have, I want to see the array get function. Array get of an array of strings, which then again contain arrays. Okay, and we are given, first of all, an array with start, len, and buffer, alright, and an index. Yeah, we check that the index is valid. Fair if it's not, then we crash. Okay, fair enough. Then we compare the ints, some other guard checks for the range, and that the index is valid. Okay, then we get the buffer. Yeah, the start. Yeah, we add the start and our index. We load the item from the buffer. And this is a buffer of arrays of strings, basically. At that index. Alright, yeah, we dupe that string. And then we drop the surrounding buffer. That does make sense. All right. Let's see where we are in here. We allocate the lambda, we allocate the array. We allocate height. Then we free the closure for generating the array, so the array has now been, successfully created. And then we are freeing the array because we've kind of retrieved the inner high from there. Boom. Things go wrong. I'm assuming that this doesn't work. I'm just putting high in here instead. It does. Interesting. Do we even need the array? That is interesting. That is really interesting. Okay, we don't need explicit arrays, we just need strings. What? I thought this was minimal, but yeah, this is, wow. Yeah, also a lot shorter. Alright, let's look at some of the compiler stages. Yeah, this just creates a string, wraps that in a sum, and then switches on that. If that is sum, the only possible thing it can be, with some string, then it creates another string, an empty string, and it returns that. Alright, that should work. So here we drop the original argument to the main function, sure. We create a string, hi, we wrap that in a sum, yeah, and we switch on that. Alright, then in this case, we want to get the string and drop the surrounding sum. So we dupe that inner string, we drop the surrounding sum, and then because we don't use the string in the rest of the body, then we actually also drop the string. Fair enough. Then in the pesto, we have some more functions, but not as much as before. So we create a new buffer of bytes of length 2. We store these bytes to that buffer. We create a 0 and a 2, and boom, this is our array. Put that in a struct. We have this sum. And then we switch on that. We dupe the payload, we drop the surrounding sum, and then we drop the payload. So far, so reasonable. I think this is where things go wrong, maybe. So let's see. How does that work? We do some... Yeah, let's look at duping and dropping, first of all, strings, and then this kind of sum thing. Or maybe buffers first, yeah. So duping a buffer Now we have a drop buffer of items. We have nothing for duping a buffer, I mean, sure, also fine. But we have something for duping an array of bytes. That takes this buffer, and then we do increment reference count of that buffer. Seems reasonable. Then dropping an array of bytes is up here. That gets the buffer. And then we call drop buffer of bytes of that buffer. Drop bytes is defined down here. Dropping a buffer of bytes. It decrements the reference count. If that is then equal to 0, then we actually go through the buffer and drop the individual items. So we create this struct containing a cursor, initially 0, and the buffer pointer. Yeah, and then we call drop buffer of byte items, and in the end we free the buffer. Seems reasonable. Drop buffer of byte items. Here. Yeah, we have a buffer, we have a cursor, and then we get the length of the buffer. If the cursor is less than that, we need to do something, otherwise we're done. And here we load that byte, because that's a buffer of bytes, at the index 2, which is the cursor from the buffer. Alright. And then we add 1 to our cursor and call ourselves recursively with cursor plus 1 with the same buffer. Yeah. Alright, we have arrays. I'm fine with that. Now let's look at strings that build on arrays. So for strings we have this dupe function, which literally just gets the array out of there. It calls dupe array of bytes. Fair enough. And then dropping a string is just getting the array out of there, calling drop the array of bytes. Makes sense. Okay, so now we've looked at this, at this, at this, at this, at this. And at this. What's remaining is this one and the main function. Actually, I looked at the main function as well. So dropping this sum switches on it. All right. And if that is sum string, then we drop that string. That also seems reasonable. Well, that is weird. Let's maybe pipe that to a file. First removing the output so that it's recompiled. Kind of look side by side at the actual execution trace and then what is supposed to happen. Okay, so first thing we want to do is create a new buffer of length 2. And then storing 2 bytes in there. Length. New buffer of bytes. Yeah, which essentially means buffer containing a ref count and a length, and then the actual bytes, aka 16 bytes. Okay. D3 was storing something, so we store something in there, and then at some point we call. Is F1 a call, or is that a jump table? I think that's a jump table actually. Yeah, okay. So we are jumping to here. And then we want to dupe the contained string. We do that here. We dupe the string. Calling dupe of that in here. Alright. Yeah, getting the UTF-8 bytes. This only consists of that. That calls dupe array of bytes, so there's an immediate call afterwards. Alright. And that increments the reference count, okay. It sets something here. Or it loads something and then it stores something. Seems reasonable. Then it returns, then the surrounding dupe of the string returns back to the main function. Okay, where we now want to drop that maybe. So we push some things to the stack, and then we call drop, which goes in here and actually switches on the enum if that is 0. And this is just some pushing stuff. That calls drop that string, please. The inner string, yeah. Here. Drop the inner string, that's up here. That just gets the bytes and then calls drop array. Boom, this one right here. Drop an array of bytes. Drop array of byte, where's that? Here. Yeah, that gets the buffer. And then it calls drop buffer of bytes, please. Boom. Alright. Now I'm going through this a bit more carefully because we're almost at the crash site. So dropping a buffer of bytes. First of all, we want to decrement the reference count. I think that already fails. Because in here, I'm dropping a buffer of bytes. Here. Dropping the reference count actually translates to loading the byte, so pushing the byte, loading that, not sure about that one. Drop buffer. Oh, I see, this is probably I'm wondering what's going on here. Because this shouldn't need to do anything. And then here the first thing we do is push that again. That would be kind of a C4 maybe. Yeah. But this is an add instruction, and that doesn't come until somewhere later. It sucks that this is so low level. You know what, let's print the stack maybe. Just so we can see a bit more of what's going on. Yeah. Oh, I see. Okay. On the stack there's a 5, the argument to the main function. Then we want to create a new buffer. So we create 16. That's the size. That's the base overhead of the buffer. We have the size of the buffer, that is 2 items long. And because this is a buffer of bytes, every item is 1 byte. We multiply those to get 2 bytes. We add those to get a total of 18 and hexadecimal 12. Alright. And then push the alignment of the buffer, that is 8. And we allocate the memory for that. Perfect. Then storing something into the buffer. That means, well, first of all, we've allocated something. This is the address of the buffer. Alright. 18E5 something. Alright, we push that again. Yeah, we push a 1. We store that in there because that's a reference card of 1. We push the address again. We push an 8-byte offset. We add those. Boom, get a new address. We add a 2, that's the length of the buffer. We store that there. Then we push that again. We store 16 there. We add those. And we do an store bytes instruction that stores multiple bytes in there. Alright, we've stored those bytes. Then we want to wrap that in a maybe, I think. Oh, I see, we first want to create the struct here, consisting of the buffer and the start and the length. So, I think the order is buffer, length, and then start. Yeah. So we push the buffer, we put the push the length, and then the start offset within the buffer. Okay. Clean. Then we wrap that in a sum, aka we just push a 0. Then we pop something below the top. Okay, sure. We have the 0, we do a switch on that. We land in the sum case. So far so good. So first we want to dupe that string. This is our string, like a pointer to the string. In order to call the dupe function, we need to push, have the correct array encoding, which consists of the buffer, then the length, and then the offset within that. Then C1 for some reason. I don't get that. And this is fine, this is the string. Then we push a byte. Oh, I see. Yeah, we get that entire sum thingy on the stack. Boom, that is a sum of string. And then in order to extract the string, we pop the top byte again. I see. And then we call dupe on that string, which is somewhere up here and here. And that means we just call dupe on that array of bytes. Alright. And that just increments the reference count. So it pushes the pointer to the stack. And another time, and another time, for some reason. Then it has this 0 here. It adds that, sure you can do that. And then it loads the current reference count, which is 1. Perfect. And then it does, what does that do? It pops something below here. Sure. Yeah. Then it pops. Then it pushes another 1. It adds those 2 for the new reference count of 2, because we're currently duping that string. Then it pushes a 0. And it pops something from the back there. What's going on here? We have the important thing is we have a pointer and we have the new reference count. Pointer points to the string buffer, and then we store the new reference count there. Oh, I see, and that pops these 2. Boom. Alright. And then we pop some more of these temporary variables. And then we return back to this dupe of the string. And that then returns back to the main function. Alright. Then in the main function, we've now duped the string, and indeed the reference count of that underlying buffer is 2 now. So what this does is it now wants to drop that maybe. So it first pushes the maybe, including the buffer and the length and the offset and the byte. Then it calls the drop function on that is defined down here. Boom. Alright, and the drop function, it first of all pushes the tag of that thing, so it can switch on that. Here it is, the tag. And it switches on that, F1, and who would have guessed we are in this case? Yeah, so we're adding some padding. We want to call drop on the underlying string, which is totally fine and should work because the reference count of that is 2, so that should now be reduced to 1. So we first push the entire string consisting of the pointer, the length, and the start offset, and then also the byte. Hang on. Oh, look at that. Well, that doesn't make any sense. We call this drop function. That expects a string, and we call that with 0, which is some string. So yeah, when we call that function, the stack is like totally misaligned. Oh no. Yeah, that calls some other function, and that let's see how that goes wrong exactly. We say drop this string, please. And that again calls the drop function here. All right. Yeah, dropping an array of bytes that was defined somewhere down here. Oh, maybe not. Oh, yeah. Yeah, and that calls drop buffer. Okay, things go wrong. Okay, fair enough. That is not surprising given that the entire address is now kind of weird with this 2 and shifted and whatnot. Yeah, this is just dropping this enum. Doesn't work. Huh. Hang on, we have dupe, we have drop. Dropping an enum. We have the value right here. Alright, and we get the payload type. We know that's an enum. We get the variant, the current variant key. We create a builder there. Alright, if that's a pointer, then we decrement the reference count of that pointer. Otherwise, we do build a drop of the value, but that's not the payload, that's the original enum value. Does that work? Or does that segfault? It works. Alright. that was painful, honestly. That was like, what, 2 hours? OBS says I've basically been recording for 2 hours now. And I think the majority of the time was reducing the example program and going through bytecode logs manually. Whew! Man, for this fix, one line changing value to builder.parent. Oh man. Oh. Okay. Let's maybe revert some of these changes and then in the playground and instead use the map here. So I want some sort of empty map. Oh, hang on, there was like even map.plum. Yeah, empty int map. We have that. That's what I want. Empty int map. Taking some type. And then I want to create a map. That is an empty int map, mapping to a string. And then I want to do map.put, and like 2 also put on a map of key value with a key and value, please. And probably the standard library doesn't export the int map. And we'll need a type. And the map type. All right. Yeah. Let's just return high for now. Works, I guess. Oh, before getting into maps, let's try that list 123 dot join. I will dot iterate. Join probably takes something else, like an iterator of strings. True. That makes sense. Yeah, and that is not an iterator of strings. That, yeah. High and there. Yeah. All right. Still got stuff to do. Wondering whether I should do that now. Let's maybe look at the allocations, just for fun, I guess. Oh, right. Alright, we allocate something. That's the string high, probably. We allocate a lambda. Empty buffer. Free the lambda. Then we reserve enough memory in the list, so we allocate more memory. I think that's just the lambda. That is the memory. Then we are freeing the lambda, and we are freeing the original buffer, because that has been copied to the new one. Alright. Then we are again allocating stuff there. Yeah, maybe not. Not today. Hi, I didn't record the rest of the bug fixes, but basically what I did is two things. First, dropping closures had a bug, because here we tried to free memory, treating that as the type of just the closure pointer instead of the actual like layout of the closure behind that. That resulted in some mismatched trees, and then also I added canonicalization of types. So basically we kind of moving this Plum type, moving that into the egg, calling that egg type, and splitting up the function. Like we had this, what was it? This type file. Yeah, here that was like hundreds, literally hundreds of lines. I split it up into multiple files. So we now have separate files for example, building a type, collecting type variables of a type, comparing two types, extending a type, and so on. And also canonicalizing types. Because I realized that in some cases we had a type like this. We have an enum that is A or B, and then that contains an enum that is A or B, and then is recursive 2 layers up, so back here. Or even just 1 layer up here. Now these get minimized into kind of a minimal representation by, well, for each recursive type that this contains, we basically try replacing the parent type with that. So in this case, you're replacing this one, this entire thing here, with that same recursive type, and seeing if that is still the same type. Yeah. And then I implemented maps, but I'll rather show that directly than in the diff. So you can now use maps like this. This creates a map from int to string. I may add a better constructor function for that. Yeah, here we put an item in there. Under the key 3, we save the string high, and then we get that out again. And when you run that, it prints high. Fair enough. And the way that works is we have this map with an array of buckets, also stores the number of items and the hash and equals function. And these buckets, I added this tombstone variant. So a bucket can either be filled, which means an item is in there. It can be, this bucket is empty, there is nothing in there. And it can be tombstone, which means that there is nothing in here, but previously this bucket was filled with something. That is required for efficiently being able to remove items from the map. Alright. Yeah, and all these functions like put and get and remove, they just linearly kind of go through the map looking for the corresponding entry. And only the starting position is determined by the hash of the key. I looked at how Zig does that, and that's pretty similar. So in the put case, we just desugar that into the entry that we want to put in there into the key and value, and we call this put function with key and value, and that make sure that there's enough space in the buckets, that we have enough buckets, and then it, well, destructures that map into its components. It hashes the key, that is going to be the kind of first index that we look into, and then it calls raw put, that returns a new array of buckets that we then put into a new map. And what this does is it calculates the index, which is the index that we were given modulo the bucket's length, to make sure that that's within the bounds. It tries to get that bucket, and this is a really cool pattern, I think. Rather than just matching over that and then doing stuff, it matches over that and then creates this enum that is a very high-level description of what we want to do. For example, if we want to put something into a map and there is already something there in the bucket that we want, then we'll just skip that and go to the next bucket and try to put that in there. But if that bucket is empty or a tombstone, then we can use that bucket. And this skip and use enum that will then immediately switch on and will do the corresponding action. But I think this is really cool, this pattern of gathering information from something, turning that into a high-level, readable description of what we want to do, and then switching on that and actually doing the low-level stuff. That is, like this, you wouldn't do this in Rust or any language where you have to declare types explicitly. This is only possible to do in such a concise way because you can just immediately have these enum literals and they get joined with like type inference and stuff. Yeah. And the same is for getting an like what this does, using that bucket just sets the bucket to a filled bucket with a key and value, and skipping that moves on to the next bucket by calling ourselves recursively with the index +1 modulo the bucket's length. Then yeah, getting pretty similar. We basically go over the buckets, and this can either be we found the item, or we don't, like we should not look into the next bucket, then we skip the item. And it can be that the item is not in the map, that we've determined that. As soon as we hit an empty bucket, we know that it's not in the map. But if we hit a filled bucket that doesn't match, or a tombstone bucket, which means that this item here got removed before, then our item may still be further back in the map, in the buckets list. Yeah, so that's maps. Yeah, regarding these constructors for common key types, I may add some more there. I may add some better, like more readable constructors there. But for now, I'm happy that it works at all. And yeah, I have maps. That's cool. So that's it for this video, I guess. And see you in the next one.